I'm Ben Craig. I'm going to take over the chairing for the debate and then for the two presentations following that prior to lunch. Let me quickly introduce our two speakers today and the format that we'll be taking. So first of all, we've got Roger Hollies, who's representing batteries. Roger has spent the past 14 years working in the energy sector, developing and delivering innovative energy solutions to solve what he sees as one of the greatest challenges facing humanity today: the rapid development of affordable and sustainable energy systems. In 2015, he joined Arenco and has seen the company grow from 2 to 30 people and now sits as the company Chief Technical Officer. Arenco has been controlling grid-scale battery assets since 2016 with their market-leading software and hardware solutions, and they're currently on the front line delivering battery assets into developing markets on the road to zero carbon. Representing hydrogen, we have Graham Cooley of ITM Power. Graham joined ITM Power as 2009. ITM Power was the first hydrogen-related company to be listed on the London stock market and has been developing electrolyser equipment for over 20 years. Graham started his career in the power sector in 1989, joined the CEGB and became Business Development Manager at National Power PLC and then International Power PLC, developing energy storage and generation technologies. Before joining ITM Power, Graham was CEO of Sensitech Limited, founding CEO of Metalysys Limited, a spin-out from Cambridge University, and founding CEO of Antonova Limited. Graham has a PhD in physics, an MBA, and is a fellow of the Institute of Metals, Minerals and Mining. Graham also sits on a number of industry bodies and is a member of UK Government's Hydrogen Advisory Council. Now, openly admitting up front that most people in the audience will not be actually perceiving this, the future, to be an actual choice between batteries and hydrogen, but rather some combination of both. For the nature of today's debate, we have artificially separated the two and basically posed them against each other. Each speaker will have 10 minutes to sell their particular technology. There'll be a further 10 minutes after that for debate, and then 2 minutes each after that to summarize each side of the argument, and then we will hold a poll. And the question of the poll is, for the whole audience, which of hydrogen or batteries do you believe will be globally carrying the most gigawatt hours of energy by 2050 as an energy storage vector? So should we start with batteries?
Yep, fine. I'm quite enjoying how different I look to my picture that I got sent over.
And me.
Lockdown has either been kind or not. I'll leave that maybe for another debate. Okay, batteries, why batteries are amazing in 10 minutes. It's a tough one. So I think we all agree that, well, decarbonising the electrical system and the electrification of transport and heating is critical for the UK to hit its future decarbonisation targets. There are areas that you could use alternatives for electrification, but for me, I think it's the simplest path and the clearest to take us where we need to go. We have the infrastructure in place, it just needs to be built out. So this year we're already on the way for decarbonisation. This year we've hit lots and lots of records, the most wind, the most solar, the most percentage of renewables on the grid, with at times over 60% being provided by renewables. And energy storage is already playing a key part. Battery energy storage is already playing a key part to this. So there's already a gigawatt of energy storage in the form of batteries installed in the grid in the UK. And I believe that that's going to easily double in 2021. And I think by 2030, by the late 2020s, I think we're going to have 10 gigawatts of battery energy storage specifically, which is a lot of energy storage. And I'm going to make a prediction here, which I've been mulling over in my head. I think before the end of this decade, we are going to see a zero carbon grid. Now, I'm not saying for a prolonged period, like a percentage of a day, but I think for an hour, I think we're going to see a zero carbon grid with enough renewables and enough energy storage. Now, it's arguable about what is zero carbon if you're using storage, because you might be using energy that's been generated in a previous time. But I think that by this operationally, we're going to see a zero carbon, 0 grams per CO2 per kilowatt hour. And that's really exciting for me. So I've got a few bets with people that that's going to happen, but I'll put it out there publicly today. So Why batteries? So Arenco are a software and automation controls company. We set up to control flexible assets into markets. We specialize in understanding the assets and understanding the markets. Now, as our COO, Mike, has said more than once, we don't care if they put bananas in these things as long as they can do what we want them to do. Like it could be any technology there, but batteries are really hitting the mark. They're fast, they're accurate, they're secure, and their performance to date is better than expected in terms of their cycling capability throughout the year. So operating a low carbon electricity network, I think you need three things. You could argue these are two. This is really, really simplistic. There's a really good presentation by Ro Quinn, which was for the Imperial College, Ro Quinn from National Grid. I encourage you to look it up, anybody wants the link. And it gives a really good description of the challenges that National Grid face in terms of operating the system. But from my simplistic view, you need to match supply to demand. So you need flexible generators. Second, which is arguably the same thing, you need to match the demand to the supply. So you need flexible load, and you need a host of power quality control. Now there's a huge list of that, and it's very, very detailed in terms of the finer detail of how you control electricity networks, but I'm just going to focus on reactive power as the main requirement to maintain voltage across the grid. Batteries as electronic power control can do all three things. They can do them efficiently, they can do them accurately, and best of all, they can do them pretty much at the same time. So if we zoom in on some of the markets that are there for these things and why energy storage is so good. At the front end of managing the supply and demand, you've got frequency response and inertia. So frequency response, you probably all know, frequency of the grid runs at 50 hertz. If the frequency goes up, the system's got too much power, so you need to take power from it. If the frequency goes down, you need to inject power into it. So these frequency response markets are now completely dominated by batteries because they're very, very good at frequency response. They're fast, as I said, and they're accurate, and they provide the service from a standing start, which I'll come back to later on, but it's a really important point. They don't need to be turned on, they're just on. So there was a new frequency response market launched in October called Dynamic Containment. We've been in this from day one and working with National Grid to develop it. We've pre-qualified a number of assets into this market, and it's like a world-leading, very difficult response to deliver. National Grid have made it quite difficult for assets to deliver it, to make sure that it's a very high-quality service. In order to pre-qualify for those services, we've had to slow the response speed of the batteries down by over a quarter of a second. These assets are really quick. So even in a post fault, which has to be fast and really sudden, because if there's a sudden loss of demand or sudden loss of load on the system, these assets have to respond extremely quickly. But National Grid don't want it too quick, and we've had to slow these assets down by between 200 and 300 milliseconds each. And that just shows me there's a lot more in the tank. So inertia at the moment is the step before that. Inertia is the characteristic which prevents the frequency from varying. I think of it as like a marble statue. If you have a big, heavy marble statue, you can push it, but it won't fall over. If you have a thin marble statue or a thin paper statue, a thin grid without much weight, you push it, you need to support it to stop it falling over. So inertia is this characteristic of spinning generation that at the moment is only recognized from spinning generation. However, you can see by this, we're slowing these things down by 300 milliseconds. If we're allowed to operate them quickly and there is dynamic inertia response, and it's been proven to work globally, I think batteries again will move into that area and disrupt the spinning generation and start providing inertia services. There's a few other points around why digital inertia could be considered better than actual inertia, but I don't have time to go into that right now. So the other aspect I talked about was reactive power. So reactive power is critical to grid stability, maintaining voltage across the networks, and And batteries essentially provide two things. They provide active power and reactive power over time. And one of the key aspects of the power control systems is that they can do that completely independently. So we ran a test where we ran a frequency response profile, and at the same time we ran a voltage response profile. So active power is responding to frequency and reactive power is responding to voltage. So we had two different control loops from one asset controlling two different things with very little impact between the two. There was a little bit of an efficiency decrease, but reactive power capability of batteries at the moment isn't even being used. It's not even being monetized at the moment, but it's definitely going to come, especially when we've got 10 gigawatts of energy storage across the network. The marginal cost of providing reactive services, voltage support, is going to be significant. There are other technologies that can do it, but the key thing, and I'll say it again, batteries, is you can stack services really, really well. So moving back to the active power side, so we've got the frequency response, high speed and inertia, then we've got the reactive power, then you've got the slightly longer time frames, which is system balancing. So the main energy markets close an hour before delivery, and then in that time, National Grid balance the system using something called the balancing mechanism. It's been talked about this over these past 2 days a few times. The balancing mechanism is dominated at the moment by gas turbines. And the key thing and basically gas turbines are paid to come on. And then once they're at their stable operating limit, they can move up and down. Provide more power and provide less power. The issue is that you have to bring them on in the first place and pay for them. So we were discussing this earlier. There was a period in May where we had a really low demand on the system. And during that period, National Grid had to bring gas on. And in order to do that, they paid wind turbines to turn off. And they also paid Europe to take energy so that we could create the headroom to bring on the gas.
1 minute left, Roger.
Say again?
1 minute left.
1 minute left. Okay. So the key point is we ran a trial and energy storage, because it doesn't have to turn on, it could provide that service 7 times cheaper than gas. So the balancing mechanism, which is a multi-gigawatt market, is going to get completely disrupted, I think, this year with energy storage, and then that's just going to get built out. So energy storage is going to dominate in that area. And the very cool thing is you can do that energy balancing. You can do frequency response at the same time because you provide the response, the small response power on top of large shifts of energy. And at the same time, you can provide reactive power services. So I think for those reasons, batteries are going to dominate. The downsides of batteries, I would say, are that they can't store energy for long periods. They're machines that are used for cycling within day multiple times. And we still have this issue of being able to time shift. If we have long periods of non-windy days, we need something that can time shift that energy from A to B. And that, if that's any more than a day, then battery energy storage systems start needing some other thing that can come in and disconnect that time period. The second downside that is being worked on is the supply chain, but I believe there's lots of initiatives going on, the Cobalt Sustainability Initiative.
Okay, Roger, sorry, going to have to stop you there.
Okay.
Thank you very much indeed for that. If we could, Graham, if you'd like to talk about hydrogen.
Yeah, sure. So hello, everyone, and delighted that you're all interested in energy storage. So I actually, I started my career with the CEGB in 1989 and have worked on supercapacitors, batteries, flow cells, and hydrogen. In fact, I was the person responsible for the Regenesis project. We built 100 megawatt hours of energy storage at Little Barford, and we opened it in 1989. And actually, that record for an electrochemical device was only just beaten recently by Elon's battery, which is 129 megawatt hours. So spent a long time in energy storage. So let me just try and help you frame the question. There are lots of energy storage devices. And if you want to segment the energy storage market, you look at duration. Okay, it's very important, it's duration. So you have very, very short term energy storage devices. They're almost instantaneous, like a flywheel or like a supercapacitor. And I did actually spin a supercapacitor company out of Cambridge University, looking at very short duration energy storage. If you want an hour of energy storage, you're going to buy a battery every time. And if you want power in, power out energy storage, and you're interested in grid balancing in terms of frequency, grid balancing in terms of voltage stabilization, and if you want day, night, power in, power out energy storage, it's a battery, no doubts about it. The question is, does the world need more short-term energy storage or more long duration energy storage? Because with batteries, you do power in and power out energy storage, and it's short duration. With hydrogen, you go power in, gas out. It's called power to gas energy storage. And the storage times are incredibly long. They are seasonal. They're not only days and weeks, but months. Okay, now how do you store the energy in a battery and how do you store it with hydrogen? With a battery, you store all the energy inside the battery. And so if you want more energy storage time, you buy more and more batteries. With hydrogen, you don't do that. You buy an electrolyzer and you don't store any energy in the electrolyzer. What you do is put the electrons in, and what comes out is a renewable molecule. And you store that either in a salt cavern or in the gas grid. Now, we work with all the major gas companies. So we work with Cadent, Northern Gas Networks, we work with RWE, we work with Ørsted, looking at putting hydrogen directly into the gas grid. So you go electrons on the electricity grid. If you need to store some of those, you can do that with batteries. But if you want to export huge amounts of energy from the electricity grid, you can store it in the gas grid. Now, why is that massive duration and massive volume? The gas grid in the UK is 3 times the size of the whole electricity grid. So there are about 300 terawatt hours of energy flowing through the electricity grid. There's 900 terawatt hours per year flowing through the gas grid. So you use the gas grid as a huge buffer for the electricity grid. So short-term energy storage, you go power in, power out using a battery. If the wind is blowing in Scotland for weeks on end with more electricity than you need, you can export all of that power to the gas grid. Now, why is that good? That is called a thing called sector coupling. What you're doing then is you're joining up the dots between the problems in the electricity grid and the problems in the gas grid, because the gas grid also needs to be decarbonized. In fact, it's more of an emergency to decarbonize the gas grid than the electricity grid, because we have hardly started. So all of the gas companies around the world are looking at using green hydrogen made from renewable power to decarbonize the gas grid, which is 3 times the size of the power grid. Okay, so here's the rub. If you look at, there's an article in Bloomberg New Energy Finance called The New Super Majors. And it is all of the new renewable energy companies that are looking at turning all of their excess electrons into green molecules for the gas grid. You also have all of the molecule companies, that is the oil and gas companies, buying renewable energy assets so that they can make renewable molecules. So you've got the renewable energy companies and the oil and gas companies converging on a solution where you have renewable power, i.e. renewable electrons. You put them into the electricity grid, and you also make with them renewable molecules which go into the gas grid and into industry. And that's very important for this reason. The whole world uses energy in two forms. If you boil it down, we use energy in the form of either an electron or a molecule. And the point about molecules is that they're storable. The really difficult thing about electrons is that they're hard to store. You can shove them in a battery, but that's short duration. The reason you do power to gas energy storage is because if you take an electron and turn it into a molecule, you can easily store the molecule. And we've done that for hundreds of years. We store them in the gas grid, which is now a huge tank to put all of our excess energy from the electricity grid, store it into the gas grid. So look, I would say this. I'd say maybe you need to reframe the question. The best form of power in, power out energy storage for short duration is a battery. The best way of storing massive amounts of energy for very, very long periods of time is by using electrolysis and storing it in the gas grid. What are our targets then? So we need to decarbonize the gas grid, which is 3 times the size of the power grid, entirely by 2050. It has to be all net zero energy gas, and green hydrogen is the only one. The government's plan, I sit on the Wind Power Integration Forum and the UK government's plan for green hydrogen. And the plan is to have a massive excess of renewable power, to use hydrogen as the molecule to store it, and not only to decarbonize electricity, but also to decarbonize gas. Another point I would pick up with what Roger said, and he's absolutely right. When you look at energy storage, you need to be thinking about a battery being every day storing and discharging, whereas hydrogen is a continuous flow. So they're a different market. You can grid balance with electrolyzers. At the front end of an electrolyzer, you have an AC-DC converter, so you can absorb a leading or lagging VAR flow, so you can do voltage stabilization. You can also turn a rapid response electrolyzer on and off in less than a second. In fact, 5 cycles. So you can do frequency work. And actually you do it on the demand side because an electrolyzer is a rapid response load. So here's the example. All of the machines in the network are slowing down. They're at 50 hertz. They all slow down because the network is overloaded and it needs loads to turn off. You turn off all the electrolyzers in 1 second. Frequency begins to rise. Rising frequency is normally because you've got an increase in the amount of renewable power, which don't have as much inertia. That's when you turn all the electrolyzers on, absorbing the excess renewable power. And what do you do with the molecules that you make? You decarbonize the gas grid. And this now, we have engagement. Today at 11 o'clock, the reason I was late is we announced on the London stock market the world's largest PEM electrolyzer. So we've just sold a 24 megawatt unit, which will supply 24-hour energy storage. That is going into a project in Germany with Total, the oil and gas company. We're now a supplier to Total, to Shell, to RWE, to Iberdrola Scottish Power, to Ørsted, to Phillips 66. And there is, and also, well, a couple of other oil and gas companies I can't mention. There
Fantastic.
is a huge amount of activity. One last point, Boris's 10-point plan. Point number 1, 50 gigawatts of offshore wind. Point number 2, 5 gigawatts in the short term of hydrogen. The EU plan is funding green hydrogen to the tune of 150 billion euros over the next 10 years. That's its importance.
Fantastic. Thank you very much, both. That was absolutely brilliant. And actually, you've already, in a way, reframed the question for a lot of people, so that it's already quite obvious that you both agree that batteries are obviously ideal for within the same day storage, whereas hydrogen is potentially a really suitable energy vector for absorbing excess power, transferring that into the gas grids and so on. And it was also a very interesting point about the idea that electrolyzers could be used to balance the a leading or a lagging load on the grid as well. I hadn't actually, I wasn't aware of that. So thank you both. One of the first questions, I've got one, there's lots of questions come through. I've got one question. To what percentage do you think, Graham, that we can actually put hydrogen into the gas grid? At what point does that become unfeasible to go above a certain percentage?
So we're injecting 20% hydrogen into the gas grid as we speak in Kiel. This is with Cadent and Northern Gas Networks. 20% of 900, well, it's about 850 terawatt hours now. Actually, 50 terawatt hours per year has decreased in terms of energy efficiency, which is marvelous. So you're looking at 20% of 850 terawatt hours today. You know, the gas grid used to be 60% hydrogen. We prior to 1969, the whole gas grid was 60% hydrogen when we used town gas. To get up to 100% hydrogen, the gas grid needs sleeving, but 60% is about 400 to 500 terawatt hours. So to go from a terawatts to gigawatts, you need to divide by 7,000 hours in the year. So it's a huge number of gigawatts. Industry today in Europe, industry uses 400 terawatt hours of grey hydrogen. Right, that is 140 gigawatts of electrolysis to decarbonize that in Europe alone. That's not worldwide. And that doesn't include the gas grid. That's just industry.
Fantastic. Thank you for that. Okay, so we've got another question here. Do you think? How do you think the needs of electric vehicles have distorted the priorities in terms of addressing the grids and delayed potentially home generation from gas supply?
Yeah, is that one for me? Let me answer that, and then I'll let Roger in. Sorry, Roger, I didn't mean to jump in there. I think transport has confused everybody in terms of energy storage, and you know, everybody. Having worked in energy storage, I've spent 30 years going to EPRI conferences and all this kind of thing, and the word is energy storage, not power storage. And so when you look at energy storage, batteries is power in, power out, whereas hydrogen is power in, gas out. You're transforming, in each case, the form of energy, but with a battery, you always give electricity back. With hydrogen, you give a molecule back. So it's a different form of energy storage. With batteries, in mobility, you know, that's all about the fact that you need a different infrastructure with hydrogen. The advantages of hydrogen in transport are range and weight. So you can refuel very quickly. You can go a longer range, but most importantly, if you want to increase the range with an electric vehicle and you increase the batteries, you make the vehicle heavier. So you make it more inefficient. But I do agree with you that it confuses the issue about grid storage, because you in the future, you're going to need lots of batteries, because you're going to need lots of short-term frequency and you're going to need a lot of voltage stabilization. So there's no question about that as far as I'm concerned. Roger, sorry to interrupt.
I'll make a quick comment on that, because I don't think they confused it. I think it's an opportunity. I think if you look at the number of cars that will be plugged in, like if you've driven an electric car, you understand it. And in my opinion, like that's it for internal combustion engine. And I do think it's it for any other type of powered vehicle. I think battery-powered vehicles, including long distance. They exist. Trucks exist that can do 600 miles on a single charge that will take an hour. It's all you need. And I do think that it's going to be dominated by electric vehicles. Now, if you multiply even domestic chargers, like 7 kilowatt domestic chargers, even if you have just a fraction of the number of vehicles as electric vehicles plugged in, you have a huge amount of both power storage that batteries can provide, ancillary services like we talked, grid stability. But I do think it opens up an opportunity for alternatives to the molecule option for storage. Whether it's enough or not, I'm not sure, but I think it'll disrupt that market. What we need for this future low carbon system is a multifaceted and combined and orchestrated response where the appropriate technologies are feeding in, be it long-term storage energy or short-term. And I think there's a big gray area around EVs because of the sheer volume of energy that they could present to the grids.
I totally agree with that. Let me give you a quick example, everybody. The electricity grid's got about 300 terawatt hours flowing through it. Do you know that fuel in the UK is twice the size in terms of energy? 650 terawatt hours of fuel used. Now, if you transfer all of that to the electricity grid, you will have to dig up the roads and you will have to reinforce the low voltage network. How are you going to do that then? So we have to have a transition away from fossil fuels. I don't honestly do not care whether it's hydrogen or batteries. In fact, every hydrogen vehicle has got a battery in it and a supercapacitor in it. You use 3 energy storage devices, one for acceleration, one for very short range, and the other for long duration. But my point is this: we've just got to decarbonize transport. That is the most important thing. I don't care how we do it. It is absolutely essential that we do it. And I think we've got to do it so it accommodates all the considerations, not only of the passenger vehicle itself, but also of the energy networks.
That's fantastic. So that in itself has answered several of these questions, and I apologise to people who have asked questions. We're running out of time actually, but so what I've taken from that then is that you probably both are suggesting that electric cars with battery power are probably going to continue to dominate for the foreseeable future because they're mature. However, I guess one of the points that was raised, yes.
Before you move off that, my view is that electric vehicles for small vehicles will dominate, and I agree with Roger. Heavy vehicles, buses, trucks, and trains are moving with all the manufacturers to hydrogen. And the reason for that is that if you want to increase their range, you radically increase their weight, whereas you don't do that with hydrogen because you decouple the energy storage, the amount of energy storage. Rather than having more and more batteries, which makes them heavier, you just have a larger tank. You decouple range from weight, but you always have a battery on a fuel cell vehicle because you need the battery for the regenerative braking. So heavy vehicles, hydrogen; smaller vehicles, batteries.
I'm gonna disagree with you. I think batteries, it's going to be they can do it. The energy density is low enough. Okay. I think that's one area we can agree to disagree on. But it's going to be fun, right? It's going to be fun finding out, and the ingenuity that's going into this. Yeah. It's that area where I think there is a direct hydrogen and battery kind of competition playing out. I think it's going to be fascinating to see what technology wins out.
Yeah. So long as we get to zero emission vehicles all over the world as quickly as possible, that's the most important thing.
Insula.
So I'm glad that I'm glad you guys disagreed on something.
I thought we could.
So we're approaching the point where we need to summarise and go to the debate now. So, but I feel that the debate has naturally sort of resolved itself in a way anyway. So, basically, the summary then is that batteries are excellent on the grid for same day storage. Hydrogen and other kind of longer term energy storage is going to be the way to approach domestic heating, and gives us a way of absorbing energy and using it at a much later date or a few days later. And as for vehicles, there is some debate as to whether or not batteries can equal hydrogen in terms of specific energy for longer journeys, with Roger supporting the idea that batteries will be able to service every transport need as well as hydrogen, Graham suggesting that hydrogen will be more useful for longer journeys, particularly for larger vessels or transport forms. So I think this leads us quite neatly onto the poll now, which is a bit contrived. We'll be completely honest with you. It's a very reductionist question. But what do people believe by 2050, which of hydrogen or batteries will be storing the most kilowatt hours, gigawatt hours or terawatt hours per year globally across all applications, including all transport, electricity grids and heating? And to clarify from one of the questions, that would be energy stored and used within the same year.
Well, while that vote is going on, I just read one thing in the chat, which somebody said energy storage, because it's about joules, perhaps we should have had a third protagonist looking at thermal energy storage. And I have to say that was a very good suggestion.
Absolutely, absolutely. Because also heating is low grade, right? If you're talking about using hydrogen to produce or electrons from relatively expensive renewables generation, then you've got to question that there might be an easier way, and that might be some kind of combined heat and power, pulling the heat. I know there's a lot of heat lost in hydrogen production. Like, are we talking about just localized heat networks? There's such a world of energy efficiency that run and technologies that can be used alongside all these new low carbon solutions that I think you guys are in such an exciting spot from an engineering point of view.
Thank you. Yeah, I think you are as well. I think the whole of energy storage is so fundamentally important now.
Yeah, definitely. Agreed.
Okay. James, how are we doing on poll results? Are we able to, I know the polls, maybe I'll leave the poll running for another 30 seconds or so, and then we could...
I'm not sure if I was allowed to vote, but I voted anyway.
Oh yeah, of course you were. I think you guys are allowed to vote.
Okay, I'll just let Graham know that, just so he can chip in if he hasn't yet.
Okay,
yeah.
I will. Yeah, I have.
I think
we vote for each other, right, Graham? That's what you do, right?
Absolutely. I vote for humanity and its longevity. I think is my vote. But...
Okay, brilliant. Well, thank you both. Shall we now reveal the results of the poll?
Yeah, the poll of 51 attending, 44 have voted, and it is a 50-50 split.
No.
Wow.
Well, if that's not the result of a good debate, I don't know.
Yeah. No, that is the result of a good debate, and I think it's a good answer because you need both.
Yeah,
absolutely.
Interesting. And I think debate is designed to generate the questions. You can't answer, you can't solve the problem in a debate. The solution is going to be you guys. You're doing the research that requires that's going to be needed for us to make these decisions and choose. So I think we're all involved. That's fantastic. I love it.
Yeah, I love that outcome as well. And thanks everybody for organizing this. It's a great debate. And thank you, Roger.
Yeah, you too, Graham. And the good thing about Arenco is we're technology agnostic. So let's talk about controlling hydrogen into the markets.
Yeah. Well, the grid balancing part, we currently work with a company called Open Energy, but we'd be pleased to have a chat with you as well.
Definitely.
Perfect. Thank you very much, guys. Thank you both. Going to have to move on to the next presentation now, but I think everyone would agree that works really well. And thank you very much. That was educational for all of us.